In 2013, astronomer Roger Clowes at the University of Central Lancashire was mapping the distribution of quasars in the early universe when he discovered something that violated the fundamental principle of cosmology. A structure so vast, so impossibly large, that light would take 4 billion years to cross from one end to the other. Not a galaxy, not a cluster, a wall. A cosmic filament containing 73 quasars aligned in a coherent formation stretching across 9 billion light-years of space. They called it the Hercules-Corona Borealis Great Wall, the largest known structure in the observable universe. But the problem was not its size. The problem was that structures this large should not be able to form, because the universe has only existed for 13.8 billion years. And in that time, gravity has had a limited window to pull matter together. The equations of cosmology built on Einstein's general relativity and tested against the cosmic microwave background predict a maximum structure size of approximately 1.2 billion light-years. The Hercules-Corona Borealis Great Wall is 7 times larger than that limit, which means either our understanding of how the universe evolved is fundamentally incomplete, or this structure formed through a process we have never observed. A mechanism that operates at scales so vast that galaxies are not objects but particles, clumping together into walls and voids that span distances larger than the visible horizon of the early universe. And the most disturbing realization is not that this structure exists. It is that we only found it by accident, because we were not looking for walls. We were looking for quasars. And when we plotted them on a map, they revealed an architecture of the cosmos that no theory predicted. The universe is not uniform. This has been known since the 1980s, when astronomers began mapping the three-dimensional positions of galaxies and discovered that they are not scattered randomly through space. They cluster. They form groups, bound by gravity, hundreds of galaxies orbiting a common center of mass. Those groups merge into larger clusters, thousands of galaxies spanning tens of millions of light-years. And those clusters connect into superclusters, filaments of galaxies threading through the cosmic web like neural pathways in a brain. The cosmic web is the largest organizational structure in the universe. Filaments of dark matter and galaxies separated by vast voids where almost nothing exists. And the shape of this web was determined in the first moments after the Big Bang, when quantum fluctuations in the primordial density field created tiny variations in the distribution of matter seeds that gravity amplified over billions of years into the galaxies and clusters we observe today. But cosmology has a rule, a principle called the cosmological principle, which states that on the largest scales, the universe must be homogeneous and isotropic. Homogeneous means that matter is distributed uniformly on average. Isotropic means that the universe looks the same in all directions. No structure should dominate. No region should be fundamentally different from any other. This principle is not arbitrary. It is necessary. Because if the universe were not homogeneous, if massive structures could form that span a significant fraction of the observable universe, then general relativity's cosmological solutions would break down. The universe would not expand uniformly. Space-time would be warped on scales where our models assume it is smooth. And the cosmological principle predicts a maximum structure size of approximately 1.2 billion light-years, a limit derived from the speed of light and the age of the universe. Beyond that scale, matter has not had enough time to communicate gravitationally, to collapse and organize into coherent structures. The Hercules-Corona Borealis Great Wall exceeds this limit by a factor of 7, which means it should not exist. And yet it does. The discovery began with quasars. Quasars are the most luminous objects in the universe. Supermassive black holes at the centers of distant galaxies actively consuming matter and emitting radiation so intense they outshine every star in their host galaxy combined. They are visible across billions of light-years, making them ideal tracers of large-scale structure in the early universe. In 2013, astronomer Roger Clowes was analyzing data from the Sloan Digital Sky Survey, a comprehensive map of the universe that has cataloged positions and distances for hundreds of millions of galaxies and quasars. Clowes was studying the distribution of quasars at redshifts between 1.6 and 2.1, corresponding to a time when the universe was between 2 and 3 billion years old, less than a quarter of its current age. He noticed that 73 quasars in the constellation Hercules-Corona Borealis were not randomly distributed. They were aligned, clustered in a coherent structure that stretched across 9 billion light-years of space and was approximately 7 billion light-years wide. The structure was not spherical like a cluster. It was elongated, filamentary, a wall of quasars embedded in a larger network of galaxies. Clowes calculated the probability that this alignment was random. The result was less than 1 in 1,000. The structure was real. But quasars are not permanent. They are transient phenomena, active only when a supermassive black hole is feeding. The fact that 73 quasars were all active at the same time, in the same region of space, suggested that something triggered their activity simultaneously. Either a massive inflow of gas, or a gravitational disturbance, or some large-scale environmental effect that caused multiple galaxies to start feeding their central black holes within a cosmologically short time window. And then in 2015, astronomers Istvan Horvath and John Hakila published a study analyzing gamma bursts, the most energetic explosions in the universe, caused by the collapse of massive stars or the merger of neutron stars. They found that gamma-ray bursts in the same region of sky as the Hercules-Corona Borealis Great Wall were also clustering, not randomly distributed but aligned in a way that suggested they were tracing the same underlying structure. This was independent confirmation. Quasars and gamma-ray bursts, two completely different types of objects detected by different telescopes using different methods, both revealing the same cosmic wall. But the size of the structure created a problem. Because the cosmic microwave background, the afterglow of the Big Bang, shows that the early universe was remarkably smooth. Temperature variations in the microwave background are only 1 part in 100,000, meaning the density fluctuations that seeded galaxy formation were tiny, barely perceptible ripples in an otherwise uniform sea of matter and energy. Those ripples grew over time as gravity amplified them. The growth rate is constrained by physics. Denser regions attract more matter, becoming denser still, while under dense regions lose matter and become voids. This process is predictable, governed by equations that relate the initial fluctuations to the final structures we observe today. And those equations predict that by the time the universe was 3 billion years old, the largest structures should be no more than 1.2 billion light-years across. The Hercules-Corona Borealis Great Wall is 7.5 times larger. Why did gravity organize matter into a structure larger than physics allows? Until now, this looked like an observational outlier, statistical anomaly, a region of the universe that happened to cluster more than average, creating the appearance of a wall where none fundamentally existed. But it was not an outlier. Because in 2003, long before the Hercules-Corona Borealis Great Wall was discovered, astronomers had already found another structure that violated the same cosmological limit. The Sloan Great Wall, discovered by astronomer J. Richard Godfrey at Princeton University, is a filament of galaxies stretching 1.37 billion light-years across space, exceeding the theoretical maximum by a small but significant margin. And in 1989, astronomers Margaret Geller and John Huckra at Harvard-Smithsonian Center for Astrophysics discovered the first Great Wall, the CFA-2 Great Wall, a sheet of galaxies spanning 500 million light-years, the largest structure known at the time. These discoveries were dismissed as edge cases, structures that pushed the limits of what cosmology allowed, but did not fundamentally break the models. Because the cosmological principle is not a strict boundary. It is a statistical expectation. Rare fluctuations, unlikely but not impossible, can create structures slightly larger than the average maximum. But the Hercules-Corona Borealis Great Wall is not slightly larger. It is 7 times larger. And it is not alone. In 2021, astronomers analyzing data from the Dark Energy Spectroscopic Instrument, DESI, a survey designed to map the three-dimensional distribution of galaxies with unprecedented precision, discovered additional filaments in the early universe that exceed the cosmological limit, not by small margins, by factors of 3, 4, 5 times the predicted maximum. This is the hidden barrier. The assumption that the cosmological principle holds at all scales. Because if structures can form larger than the homogeneity scale, if the universe is fundamentally clumpy, even at distances where it should be smooth, then the entire framework of cosmology is incomplete. And then in 2022, astrophysicist Alexia Lopez at the University of Central Lancashire working with Roger Clowes, discovered an even larger structure. The Big Ring, a near-perfect circular arrangement of galaxies spanning 1.3 billion light-years in diameter, located in the constellation. Boats at a distance of 9.2 billion light-years from Earth. The structure is not a wall, but a ring, a geometry that no known cosmological process can produce. Lopez analyzed the statistical likelihood that galaxies would randomly arrange themselves in a circle this size. The probability was less than 1 in 10,000 the ring was real. But nothing in the standard model of cosmology predicts circular structures at these scales. Gravity does not create rings. It creates spheres, ellipsoids, filaments. Circular structures require rotation, or a central void, or some organizing principle that operates over billions of light years. And no such principle exists in standard cosmological models. Why does the universe contain geometries that gravity alone cannot explain? In 2023, cosmologist Sabir Sarkar at the University of Oxford published a controversial paper suggesting that the cosmological principle might be wrong. It's not slightly inaccurate, fundamentally incorrect. He analyzed the distribution of galaxies in large-scale surveys and found that the universe is not isotropic. There is a preferred direction, a cosmic axis along which structures are aligned, as if the universe has a grain, a built-in asymmetry that violates the assumption of uniformity. Sarkar's analysis was disputed. Other cosmologists argued that the apparent anisotropy was an artifact of observational bias, that the regions of sky surveyed were not representative of the universe as a whole. But the debate revealed a deeper problem. We do not know if the cosmological principle is true. We assume it because the alternative is too complex to model. Because if the universe is not homogeneous on the largest scales, then our measurements of dark energy, dark matter, and the expansion rate of the universe are all systematically wrong. Every cosmological parameter derived from the cosmic microwave background assumes that the universe is smooth, on scales larger than 1 billion light years. If that assumption is false, then the entire cosmological model needs to be rebuilt. In 2024, astronomers using the Euclid Space Telescope, a European Space Agency mission designed to map the geometry of the dark universe, completed the first year of observations. Euclid's wide-field camera captured images of billions of galaxies, measuring their positions, shapes, and distances with unprecedented accuracy. And when cosmologist Yannick Malier at the Institut d'Astrophysique de Paris analyzed the data, he found something that no previous survey had detected. The cosmic web is not random, it is organized. Filaments do not intersect chaotically. They connect at nodes, massive clusters of galaxies where multiple filaments meet, like intersections in a highway network. And the spacing between these nodes is not arbitrary. It follows a pattern, a characteristic scale of approximately 500 million light-years, repeated across the observable universe. This was unexpected. It's because if the cosmic web has a preferred scale, a repeating structural motif, it suggests that the initial conditions of the universe were not purely random. Something imprinted a pattern into the density field before galaxies formed. A template that gravity followed as it assembled matter into the structures we observe today. Melier's team ran simulations to determine what could create this pattern. They tested models with different amounts of dark matter, different expansion histories, different initial fluctuation spectra. None of them reproduced the observed regularity. The cosmic web was more ordered than any model predicted. And then cosmologist Pavel Naselsky at the Niels Bohr Institute in Copenhagen proposed an explanation. He suggested that the pattern was not created by gravity alone, but by sound waves in the primordial plasma. Acoustic oscillations that propagated through the universe in the first 380 years after the Big Bang, before atoms formed and photons decoupled from matter. These sound waves left an imprint on the cosmic microwave background. A pattern of hot and cold spots that corresponds to regions where the plasma was compressed or rarefied by the acoustic oscillations. And those same oscillations would have seeded the formation of the cosmic web, creating a preferred scale where filaments are most likely to form. Naselsky's model predicted that the largest structures in the universe should align with the acoustic scale of the early universe. Amplified by billions of years of gravitational growth, The Hercules-Corona Borealis Great Wall, the Big Ring, the Sloan Great Wall, all of them could be explained as rare but possible fluctuations in the primordial soundfield regions where the acoustic waves constructively interfered to create overdensities larger than the statistical average. But the model had a problem. It required that the acoustic oscillations in the early universe were far more coherent than the cosmic microwave background suggests. The temperature fluctuations we observe are tiny. It's too small to seed structures as large as the Hercules-Corona Borealis Great Wall, unless something amplified them, something that increased the amplitude of the density fluctuations. After the cosmic microwave background was emitted, but before galaxies formed, and the only known mechanism that could do this is inflation. The theory that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. Inflation stretched quantum fluctuations to cosmic scales, creating the density variations that became galaxies. But standard inflationary models predict a smooth Gaussian distribution of fluctuations. They do not predict giant walls or rings, which means either inflation was not smooth, or something else happened in the early universe that we have not yet discovered. A phase transition, a symmetry breaking, a moment when the laws of physics changed, imprinting a pattern into the fabric of space-time that we are only now beginning to see. In 2013, Roger Clowes discovered a wall of galaxies 9 billion light-years long. He did not know he was challenging the most fundamental assumption in cosmology. He thought he was mapping quasars, cataloging the positions of distant objects to understand how the universe evolved. 11 years later, the structure has not been explained. Not by gravity alone, not by acoustic oscillations, not by any mechanism in the standard cosmological model. The Hercules-Corona Borealis Great Wall exists, and it is not alone. The Big Ring, the Sloan Great Wall, the CFA2 Great Wall, all of them point to the same conclusion. The universe is not as homogeneous as we thought. It is not smooth on the largest scales. It is clumpy, structured, organized in ways that violate the cosmological principle. And if that principle is wrong, then everything built on top of it, every measurement of dark energy, every prediction of the universe's fate, every conclusion about how the cosmos began, must be reconsidered. Because the cosmological principle is not just an assumption. It is the foundation. It is what allows cosmologists to use general relativity to model the universe as a whole, to treat space-time as a smooth background that evolves predictably. Without it, the universe becomes a chaos of local geometries, each region expanding at different rates, each structure evolving independently. And the most unsettling realization is that we only discovered these structures recently, not because they were hidden, but because we were not looking. We assumed the universe was smooth, so we built surveys designed to measure average properties, not extreme outliers. We averaged over large scales, smoothing out the very structures we should have been studying. How many other walls exist that we have not found? How many rings? How many filaments? How many cosmic architectures are waiting in the data? Invisible, because we are not asking the right questions. And once you realize that the universe contains structures larger than our models allow, that the cosmos is more organized than randomness predicts, you start to wonder if the universe is not just a product of gravity and expansion. You start to wonder if there is a template, a design, a pattern imprinted into space-time itself that we are only beginning to recognize. Subscribe to Universe Uncovered. Because the universe is not random, it is structured. And the largest structures we have found are telling us that our understanding of how it formed is incomplete.